All right, ladies and gentlemen, we are moving on in chapter 6 to section 2. We are going to talk about earthquakes, one of the things that happen on our earth caused by those plate tectonics. So, earthquake distribution. For years, scientists knew that earthquakes were not distributed randomly. This is before we had this idea of plate tectonics. And scientists for years have been mapping out kind of where are those places where we get earthquakes. Well, as they continued to map and continued to learn more about earthquakes, we really saw that for the most part they are found in defined zones. As we learned more about plate tectonics and plate boundaries and what these tectonic plates are, what we learned is that these earthquakes most often happen along those plate boundaries. So where two different plates interact, where we get those convergent, divergent, or transform plate boundaries. That's where we are most likely to have earthquakes. So let's take a look about what an earthquake is. By definition, something that you need to know, a vocab word, earthquakes. An earthquake is a sudden movement or vibration of the ground when rock slips along enormous cracks in the Earth's crust. I want you to take a few seconds and write that definition in your own words. What is an earthquake? All right. Now that you have your definition a little more, the shaking can cause. Please note it does not say will cause buildings to collapse. When buildings collapse, that's what causes most of the death and damage. It's not the earthquake. If an earthquake hits in the middle of a prairie and there is nothing there, the ground's going to shake. You might get some breakage of rocks and stuff in the area, but you're not going to have the death. You're not going to have the damage because there's nothing there. It's the collapsing of buildings that causes the death and people getting trapped inside buildings during an earthquake that cause the death and the damage. Causes of earthquakes. So when an earthquake happens, what's the process that leads up to that? Earthquakes are caused by forces that act on the rocks. Okay, that stress is built up per area on that object. We've got 4 different types of stresses. You do need to know all 4 of these: compression, tension, shear, and torsion. A compression stretch is something that's squeezed or shortened. Think of those of you that have ever had a compression wrap. And they take the ACE bandage and they wrap it super tight around, whether it's your leg, your ankle, whatever it is. And what that's doing is that's squeezing everything together so it doesn't swell up. So when a compression stretch, everything is being squeezed together. Think of it as a stress ball. If I have a stress ball in my hand and I squeeze it, it's all getting squished together. A tension stress is one that's stretched or lengthened. Think of this as your rubber band. Okay, I can take that rubber band and I can pull it and pull it and pull it. Okay, and eventually that rubber band is going to snap or it's going to bounce back. But that tension is that stretching or lengthening of a rubber band. Same thing with Play-Doh. I can take a container of Play-Doh in my hand and I can pull and pull and pull that Play-Doh. Eventually it's going to snap. Shear. Shear is when 2 objects are moving along in a plane in different directions. It's like rubbing your hands together and rubbing them back and forth. Your hands are moving in 2 different directions. That's a shear stretch. Now imagine if I put glue on your hands, it's going to get very sticky. And if I still made you move your hands back and forth, okay, eventually they're going to be trying to move in different directions and they're going to get stuck. And you have to apply more force to overcome that stuck bit. And torsion or twisted. Okay, this is when the rocks are actually getting twisted in more than one dimension. Again, going back to Play-Doh, imagine I have a piece of Play-Doh in my two hands, and I move one piece toward me and one away from me, and I am turning the two pieces of Play-Doh into different directions. So that rock is actually getting twisted. It got stuck somewhere. It's trying to subduct, but part of it is moving faster than the other. So again, compression, tension, shear, and torsion are the four types of stresses. So that stress gets built up over time. Okay, and eventually something happens. One of two things is going to happen. We're going to have elastic deformation or we're going to have plastic deformation. Elastic deformation is when that stress is applied and eventually we overcome that stress and the objects that were in the stress bounce back into their original shape. Okay, think of a rubber band. If I have a rubber band, and I let go of that rubber band, I take away that stress of it, it's going to snap back into its original shape. Plastic deformation, on the other hand, is when that stress is applied and after that stress is released, it takes on that new shape. I like to give the example here of modeling clay or Play-Doh. If I have a ball of Play-Doh sitting on my desk and I push down on the Play-Doh, okay, I've compressed it, okay, I've made it thinner, but when I lift up my hand, it's going to keep that new shape. It's not going to bounce back. It's not going to return to its original form. Okay, so elastic and plastic. I also like to think of plastic, if this helps you remember it. If I take a plastic bag and I pull it, okay, it's going to change its shape. It's going to get that wavy structure to it. Try it with a plastic lunch sandwich bag or a plastic grocery bag, and you will be able to see as you pull, and eventually it might snap completely and rip. So we've got this energy built up, and then it snaps. It either bounces back or it is permanently changed. But that energy release is sent up along the rocks. So it's built up energy within the rocks on these fault lines where the plate boundaries are coming together, or fault lines can happen whenever there is a break in a rock, that energy is released and the rock moves. It snaps back. Okay. At the fault line, the rock moves. Well, when that rock moves, okay, we get that elastic rebound. But it's the sudden release of that energy that causes then these earthquake waves to be sent out from where that energy is released. Okay, and when that energy is released, you get these earthquake waves. If I were you and you are a test taker, I would know this slide. Circle it, highlight it, can pretty much guarantee that there is a question on how does an earthquake happen. Okay? Rock has the energy built up, the energy releases. Okay, there's the fault line involved. You've got that strain energy released and then the elastic rebound, so that rock bounces back. And as it's bouncing back, it sends out those seismic waves. So, seismic wave, what are they? Again, another vocab word here. Seismic waves travel out in all directions from where that strain energy is released. So, seismic waves are the earthquake waves. Where that energy is released is called the focus. If we take where that focus is and take it right up to the surface of the earth, we have what's called the epicenter. So looking here, that focus there, you can see the red lines coming out of it. That is where that strain energy was built up. and then released. The epicenter would be the place on the actual map where we say the earthquake happened. So if an earthquake happens, you would hear something about the focus of the earthquake was 3.6 miles into the earth, 5 miles northwest of Los Angeles. Okay, that would be an example of where the focus was, how deep it was, and then where the epicenter was, how many miles outside of Los Angeles. So these seismic waves, okay, they are sorted into two major categories. We have our body waves and we have our surface waves. Two types of body waves that we are going to talk about are our primary and our secondary waves. And then we will also talk about surface waves. So let's look at primary waves first. If you're in primary school, that's your first instance of school. So primary waves are the first waves that come out from an earthquake. Okay, they travel along like a coiled spring. So if I have a slinky and I have it laying long ways on the ground and I tap one end of the slinky, you are going to see that wave move through the slinky. That is similar to how a primary wave moves through the earth. So it's this compression and release of the wave out. Okay. So it causes the particles to move back and forth along that direction of the wave. Okay, the rocks return to their original position after the wave passes. So primary waves do not really cause any damage. Okay, they pass, that's all good. Primary waves can pass through both solids and liquids. Okay, this will become important when we talk about the interior of the earth in section 3 of this chapter. Speed of primary waves is between 5 kilometers and 7 kilometers per second. They are the fastest of the earthquake waves because they are the first waves that a seismograph will pick up. Secondary waves, okay, they are the second waves on the scene, or if you are in secondary school. Okay, currently high school is a secondary school. You've finished elementary school, now you're on to this secondary education. Okay. We abbreviate secondary waves S waves. Please don't get this confused when we talk about surface waves. So when I refer to S waves, I'm referring to secondary waves. P waves, primary waves, surface waves we do not have an abbreviation for. S waves travel along like a moving rope. So if I have a piece of rope and you have one end of it and I move the rope up and down, then that wave makes its way to you. That is very similar to how a secondary wave would move. Okay? Secondary waves cause the materials to move perpendicular, so at that 90-degree angle. So if the surface or the earthquake waves are coming out from that focus and traveling up to the surface, these secondary waves are moving perpendicular to that direction. Secondary waves are going to be the second waves that a seismograph station records. S waves can only move in solids. This also is going to become very important when we talk about the interior of the earth and how we know what is there. S waves move slower than P waves. You do not need to concern yourself with time, with speed, but know that they are going to move slower than the P waves. Okay, a little bit of an example of an image. It's not animated though, so I highly suggest you get into your textbook, and if you did not watch the videos that were linked, please make sure that you do. And if for some reason the video code is not working, you can go to YouTube and search for P waves and S wave motions and get those videos. Last type of earthquake wave that we are going to talk about is surface waves. Surface waves move in a much more complex manner. Again, you are going to want to watch the video on surface waves that was in your textbook. Okay, these are often compared to what an ocean wave would move. So there's going to be this rolling. So not only is there going to be this up and down, but there's going to be this tumbling. Think of it as if you have a bunch of clothes in a washing machine or in a dryer. It's this constant tumbling and mixing. That's how a surface wave moves. They can also have a side-to-side motion. So they become very complex in nature, and when the earth is moving up and down and side to side and rolling all at the same time, you get a lot of damage. Our man-made structures are not designed to necessarily hold up to this different movements. Okay, we built the Gateway Arch in St. Louis, and if you've ever been up to it, you can feel how it is made to sway in the wind. If you've ever been up there on a windy day, you know what I'm talking about. However, if that arch was made to move up and down and side to side and rolling, you could see how it would quickly have some damage to it. So how do we measure earthquakes? You hear a lot of times on the news when an earthquake hits about it was a 4.2. Or maybe you've heard lately about an increase in 1 to 3 magnitude earthquakes happening in Oklahoma. What exactly does that mean? Well, we really have two types of scales that we use to measure earthquakes. One is the modified Mercalli scale and one is the Richter magnitude scale. Let's look at the modified Mercalli scale first. This one is not used as often because of what it's measuring. It's measuring the amount of damage that an earthquake causes. The scale ranges from 1 to 12. So here's an example of the Mercalli scale. What are some problems that could come with the modified Mercalli scale? Well, economics. Think about an earthquake that happens in Southern California versus an earthquake that would happen in the Himalayan mountains. Lots of money, lots of resources used in Southern California to build those structures versus in the Himalayan mountains, which is struck by poverty. Okay? A same earthquake intensity on the Richter scale, which we'll get to here in a minute, can cause very different damage. Okay, if you look at the earthquake that happened 7 years ago in Haiti, what that was in magnitude on the Richter scale and how much damage it caused versus that same earthquake happened in California, we probably would not have nearly as much damage because of how our buildings in the United States are made. So modified Mercalli really has a lot of social stuff. So Red Cross might use it so they know how impacted the community is by the earthquake, but scientists don't use this one as much because it doesn't compare apples to apples. What you hear more often in the news and used by seismologists is the Richter scale. And the Richter scale measures the amount of energy that is released during the earthquake. So since we're directly measuring that amount of energy, now we can compare apples to apples when it comes to earthquakes. A 6.2 Richter earthquake in California is going to be the same as a 6.2 Richter earthquake in the Himalayan mountains. How they use to measure this is using a device called a seismograph that records the vibrations produced by an earthquake. And it has a little pin on it, and as that earthquake wave comes through, you will see little marks being made on the paper. And I do believe the University of Wisconsin-Whitewater is the closest seismograph that is used by the USGS, and so it is constantly ready to go and record the seismic waves if an earthquake wave would be detected by that seismograph. Tomorrow in lab, you are going to use kind of readings used by a seismograph, recording the S waves and the P waves and the delay involved in it to determine where the epicenter of the earthquake was. With the Richter magnitude scale, so magnitude, think exponential growth. When you get into Algebra 2, you will deal with some magnitude problems as well, because I just had a conversation the other day with Mrs. B. Wells about the Richter scale and magnitude as she was using it as an example in her Algebra 2 class. So what does this mean? This means that on a scale, the difference between a 1 and a 2 is not the same as the difference between a 4 and a 5. You have exponential growth. So it's like saying 2 times 2 is 4, but 4 squared is 16. Okay, 16 squared, I don't have a calculator, so you can see how that would very quickly increase. Middle here, you can see how many earthquakes a year happen at those various levels. Now, 1, 2s, 3s, even 4s are happening all the time. Okay, we don't feel them very much, but if you went on to the USGS website right now, you could do some research on exactly those earthquakes happening right now, and you could look at how many 1s and 2s have been recorded in the last week. Even 3s and 4s recorded in the last week. Usually we don't start to hear about them in the news until about a 4 to 5 range, okay, here in the Midwest, or unless it hits a very poor region or if it hits a very populous region. Okay, 6, 7s, 8s, they're not happening nearly as often. However, I do want to inform you guys and kind of give you fair warning. I have taught this section now for 7 years, and every year when we get to this section, a fairly major 6, 7, 8 earthquake happens. So just be prepared in the news for something to happen probably here soon. Okay, so don't say I didn't warn you. Levels of destruction. So like we kind of said, the damage can greatly vary. A 6.2 in St. Louis is going to be very different than a 6.2 hitting in Haiti. Okay. Poor building construction is the largest contribution to earthquake damage. It's the reason why Haiti was pretty much wiped out by their earthquake. Today, it is possible to use high-tech materials to make a building earthquake resistant, but not earthquake proof. There's lots of building codes nowadays in these earthquake zones where those plate boundaries are that have earthquakes more often to have some give and take. The tall skyscrapers, the St. Louis Arch, they're meant to move. Okay? They're on their foundation, but they are built in a way so that they can move as those seismic waves come in. But again, we cannot make a building earthquake proof. Lots of research, lots of engineering going on right now into how do we make things more and more resistant? How can we make these materials cheaper so that areas like Haiti and the Himalayan mountains can benefit from such materials, because right now they are so expensive. So that's going to conclude our lesson for today. Make sure you are ready for lab tomorrow. Please, please, please make sure you have a calculator, because we will be adding and subtracting math, or adding and subtracting minutes and seconds, and it may just make your life a tad bit easier. If you have any questions on this section, please let me know. Thank you, and have a great rest of your day.